just a recommendation for whatever it's worth. If you're interested in a particular school, if it's within your means to do so, before you make a decision, drive over to the campus itself.
Mm-hmm.
And regardless of what college it is, there's two offices that you'd be most interested in. One of them, Fresno State calls it the evaluations office, but who knows, but anyway, it might possibly go by other names, but the evaluations office, because when you transfer to a four-year college, I know you've been through this before, where they look at your transcripts and they say, well, we'll take those classes, but then we won't take these classes.
Right.
So you need to bring an unofficial copy of your transcripts with you, and then leave them with that office, and they'll tell you whether or not they'll take however many units. The second office that you need to go to is the department of, the area of your interest, whatever your major is. You want to go to that department office because oftentimes they will have literature in that office that tells you exactly what you got to do to graduate with a bachelor's or a master's or a PhD in that program. And
Okay.
So that would be kind of nice to know.
Okay.
Yeah. And plus, for those of you who are considering graduate work, which I really do hope that the opportunity presents itself in your life to do this, but just to let you know, when you get to the graduate level of education, everybody, part of it is political. And what I mean by that is if you think you're going to go to graduate school, when you are a junior at the undergraduate level, beginning around there, you need to start networking with all the various professors. You need to make your face known, and you need to, regularly meet with these people, volunteer for something, possibly work as an aide or something like, because these are the people that are going to write your letters to get you into a graduate program. Plus, as you get to know your professors, you find out that they don't all share the same philosophy.
Oh, I bet.
Whatever the discipline is that you're looking to study. So, yeah, it's best to network.
I have a question for you that's off the subject of that.
Uh-huh.
So my son came to me last night and he says, Mom, if we were standing on one side of the universe and we went all the way through, or not the universe, I'm sorry, the Milky Way, and we just traveled all the way straight through the Milky Way, how long would it be? How long would it take at the speed of light? And so I Googled it, and Google says that it would take 200,000 years. Does that sound right?
The center of our galaxy is 26,000 light years away from here. So it would take, at the speed of light, 26,000 years to reach the center of our galaxy.
Okay,
if you wanted to go to the far, our galaxy is 100,000 light years wide. So if you wanted to cover the entire distance at the speed of light, it would still take you 100,000 years.
Okay. Yeah, because we were talking about how he's like, okay, Mom, because I told him, that we live in the Milky Way and all that stuff, and he's 10, and so he's like, okay, so if we were standing on the outer side of the Milky Way, and we just decided just to fly straight through to the other side, how long would it take? And when I Googled it, I was like, Google said 200,000 years to cross the whole galaxy. And I was like, I'm going to ask my professor about that tomorrow. That's a long time, but it's gigantic. So
Yeah. Well, this gets better. Our galaxy is 100,000 light years wide.
Mm-hmm.
That's pretty darn big. At the speed of light, it's still going to take you 100,000 years to cover the entire width of the galaxy.
Uh-huh.
Our nearest galactic neighbor is the Andromeda Galaxy, and it is right now about 2 million light years away from us.
Mm-hmm.
And that's the nearest thing to us. Well, it's about twice the size of the Milky Way galaxy. And the black hole at the center of that galaxy is a lot bigger than ours. And we are headed straight for it in a collision that will happen in the distant future.
That sounds like fun.
It's going to be a really long time because
Yeah.
we're moving toward each other at a relative speed of about 500,000 miles an hour.
Mm-hmm.
And so on a galactic scale, that's actually slow. And so it's going to take about 3 or 4 billion years before we actually collide with the galaxy.
And then I was going to ask you too, I was reading last night when I was in bed, I was trying to fall asleep. So I did the opposite of what they tell you to do about shutting your brain down. And I was looking on Facebook and I ran across this article and it was talking about that scientists are finding just like rogue planets, just like kind of floating around.
Yeah, they're not associated with a solar system at all.
Right. And I was thinking, is it just because they got slingshotted off of something and they got too far away and just kind of started floating around?
Okay. In the early days of the formation of this solar system, there's evidence to indicate that when the dust cloud first began to form into solid objects, this was after the sun was formed. We're talking about the leftover debris now. And it's beginning to accumulate into larger and larger solid objects. Well, right now we have 8 planets plus countless moons, comets, and all that kind of crap. But when you go back to the earliest days of the solar system, there was probably 30 or 40 planets going around the sun. And so they did not all have circular orbits. And so that meant that at some point there was going to be a collision. So the earliest days of our solar system, there was a lot more planets, but there was also a lot of collisions occurring and smaller objects got bigger. And so in all of this moving around in our solar system, as all these planets go around the sun, as they go around, Jupiter is the single largest planet. And it's large enough, everybody, that it does have the gravitational power to literally slingshot a Neptune-sized planet, which is 8 times the size of Earth. It can slingshot it, yes, out of the solar system. And so it's not an unusual occurrence. We've documented these rogue planets dozens of times. They're just floating free through the galaxy.
So so there is a possibility that some of these rogue planets used to be ours.
Well, at the time when they work out their mathematical models, these planets would have been slung out of our solar system probably about 3 billion years ago.
Uh-huh.
And so what that means is it happened. See, the galaxy rotates as well. And
right.
3 billion years ago, we were on the exact opposite side of the galaxy in the rotation. So if the planet got flung out in that region, who knows where it's at now? Because we've come all the way around.
Right. Yeah, I just thought that was really interesting. I'm like, man, there's just like planets just floating out there that don't really belong anywhere.
Well, yeah. Well, we've also, the other strange thing is we've also discovered whole stars doing the same thing.
Oh, wow.
And uh, there's only one object known in the universe that has enough gravity to be able to fling an entire star out of its solar system, or maybe even out of the galaxy, and that's a black hole. And that's how we discovered that the center of our galaxy is a black hole. We were looking at stars that were absolutely huge. They were 10, 20, 30 times the size of our sun, and they were being flung around on these crazy orbits. And they came to the conclusion by working out the math that there was only one thing that could be responsible for throwing dozens of stars out around this crazy orbit. It had to be a black hole. Well, about 3 years ago, a group of scientists were able to electronically, they created a telescope that had the magnifying power of the entire Earth. What they did is they connected a series of telescopes from around the world via the internet, and they all focused on one particular place, and they actually took a photograph of the black hole.
Wow.
That's never been done before. And the reason it's so remarkable, I mean, think about it. It's called a black hole for a reason. You can't, there's no light that comes out of it. The only reason you know it's there is because of the way objects behave around it.
Yeah. That's
And
crazy.
so, yeah, you have to deduce this from the math. And so the reason they were able to get a photograph is when material falls into a black hole, the black hole itself does not give off any light. Everything is gone. It's out of the universe now. But as it's spiraling down, it is moving at sizable fractions of the speed of light as it circles the black hole, about ready to be swallowed. Well, that generates a lot of heat, and heat glows. And so that's what they have a photograph of, is all of this glowing debris going around what looks like an almost perfect circle, a black dot in the middle of all that debris. And it's falling into it. You see, the mysteries of the universe oftentimes can be replicated here on this earth in a laboratory because, for instance, how did we figure out that all this debris that was circling the black hole was creating friction, which was creating heat? Well, all you got to do is rub your two hands together real hard for about 30 seconds, and you're going to heat your hands up, aren't you? Well,
Right.
that's all this debris circling around the black hole at probably 1/3 to 1/2 the speed of light. That's going to generate a lot of friction.
Right. It's so crazy.
Okay. Let me get my study guide out here and then we'll get going. Does anybody have any questions about yesterday's material at all? We're okay with this? All right. I left off explaining, let me get the recording going here.
Recording in progress.
I left off yesterday explaining to you true wind speed and true wind direction. Once again, wind only moves in one direction, and that is from areas that are higher toward areas that are lower in pressure. So wind is created by differences in air pressure, okay? So right now, we're in the middle of our summer, and we have these clear sunny days. And I told you yesterday that is associated typically with a high pressure system. Well, the Great Central Valley is dominated by a high pressure system in the summer months. I also went on to explain to you that low pressure systems are often associated with cloudy and rainy days, because in order to get it to rain on your head, everybody, air has to rise. So you've got this air that is being pushed up. In the case of the Central Valley, the air is being pushed upward along the side of the Sierra Nevada mountains. And we don't get a lot of rain, but that's how it rains here in the Central Valley. And so when these two pressure systems, they move with the seasons. So as the angle of sunlight changes on a daily basis, these pressure systems all around the globe move according to the daily change in solar angle. And so over a period of months, the high pressure system that we are currently under is going to slowly move away, and a low pressure system will start to dominate over the Great Central Valley, which means our rainy season, our winter months. But think about this, everybody. As one pressure system moves out and another one begins to move in, at some point in time, you are located directly between these two pressure systems. And I said once again, wind is created by differences in air pressure. Do you remember? If the greater the numerical difference between two pressure systems, if one of them is 1020 and the other one is 1000 millibars, that's a pretty good wind. Okay, now you are directly between these two pressure systems, which is in this case where it happens to be the windiest. And for us here in the Great Central Valley, that typically occurs around November and in about the months of March and April. So when do you fly your kites? You're in between two pressure systems. Okay, so anyway, true wind speed, true wind direction, pressure gradient. The greater the difference in the pressure gradient, the faster the wind speed. Coriolis effect was caused by the rotation of the Earth. In the northern hemisphere, it's going to deflect wind to the right. In the southern hemisphere, it will deflect wind to the left. Friction force is caused by dry land. Okay, as air passes over the oceans, there's nothing to slow it down. So you have much higher wind speeds when you are out in the middle of the ocean. Once it hits dry land, now the air has to pass over all these various mountain ranges. In our case, it's the Sierras, and then it's the Rocky Mountains before it comes crashing down into what's the central United States. This is why it's so damn cold in Denver, Colorado. It's right there on the edge of the Rocky Mountains, and you got all this cold air come rushing over, and it's dry air because it's given up all its moisture over the Sierras, what little bit over Nevada, and now it's passing over the Rockies. Oh, this is really cold air. So anyway, friction force is caused by dry land, and it slows the wind down. So the taller the mountain range, the more it will slow the wind down. Okay, Earth's wind belts. About the only test question that's going to show up is going to have to do with what wind belt is the United States located in. And we are located within the westerlies. And remember, wind is named according to where it is coming from, not where it is going. So in our particular case, the wind is coming from the direction of the Pacific Ocean, and it's passing over California on its way to New York. And it's been doing that for tens of millions of years. That hasn't changed. And that's the general wind pattern. Somebody asked me earlier about monsoon winds, and this is off the track a little bit, but it does have to do with weather. The word monsoon, everybody, is Arabic, and it merely means reversal of the wind. It does not mean a big, huge storm. It's a reversal of the wind. And the reason it's dangerous, everybody, is because, as I said, suppose, for instance, just as an example, I said that the United States is in a wind belt called the westerlies. Okay, so California is dependent on the rain that it gets from the water that is off the coast of California. That's where the rain comes from. Okay, well, let's just suppose that suddenly the wind reversed itself and now it was moving from New York toward California. It would pick up moisture over the Atlantic Ocean, and then it would rain it all out over the Appalachian Mountains, over the Midwest, over Central America, definitely over the Rocky Mountains. And by the time it got to California, there'd be hardly anything left in it. You think we're dry now? We would be a wasteland. There'd be very little water coming in. So this is why monsoon winds are dangerous. They bring with them unpredictability and in many cases, pretty much the exact opposite of what had been normal. So in our case, it's about 11 inches of rain a year, but if you reverse the wind, we get even a lot more drier, okay? And so the Native American Indians that were living here in the North American continent, they were very familiar with these winds that change directions, and they named many of them. And white settlers began adopting the usage of these names to describe these winds. And so that's what a mono wind is, everybody. It's a monsoon wind. And mono means that the wind has changed directions and it's coming from the direction of the Mono Mountains. That's all. That's all it means. There was one called the Zephyr wind. Okay, so there's different names associated with it, different cultural names, but ultimately they're all monsoon winds, and it merely means reversal of the wind. That's all it means. It's especially dangerous when you get into places like India. A monsoon wind occurred in the Bay of Bengal, which is it's on the eastern shore of India, where India and Bangladesh share a border. And there was a monsoon wind that occurred in that region of the world in 1971. And in less than 6 months, everybody, that monsoon wind dropped 450 inches of rain on top of Bangladesh. And Bangladesh is very flat. There's no mountains in Bangladesh. So when that water fell, there was no slopes. There was no way for the water to run off. So it just got deeper and deeper and deeper. And you can imagine the death toll that was associated with that. Little cultural note, that's when rock stars began getting interested in doing aid concerts, because that was one of the first big aid concerts in rock history or pop cultural history. A bunch of musicians got together to perform aid for the Bangladesh. But anyway, underneath, it says adiabatic lapse rates. Okay, this has the potential to be confusing, but you do have diagrams, and I will be more than happy to take questions after I get done explaining this. First off, I told you earlier that in order for it to rain on your head, air has to rise. Not fall down, it has to go up, okay? There are, here on the surface of Earth, there are 3 different ways air can rise. The first one is convectional lifting. And all that means, it's very simple, everybody. It just means hot air rises. Have you ever noticed in your kitchen, if you've ever paid close attention to your oven, it says that your oven is a convection oven? Well, do you know what the word convection merely means? That the heating coils are at the bottom of the oven, and so the hot air rises up through the food. That's all convection means. So you have hot air rising, okay? The second way that air can rise, and it's referred to as frontal lifting. When 2 air masses collide with each other, Assume one of them is cold and one of them is much warmer. Cold air is much heavier air. Cold air wants to sink and stay on the ground. Warm air wants to rise. When these two air masses collide with each other, the cold air mass is going to stay on the ground, and it's essentially going to push the warmer air upward. That is frontal lifting. The third way, and this is the example in the handouts that I gave you, everybody, it's called orographic lifting. Orographic lifting is air that is being forced upward along the side of a mountain. That is orographic lifting. And that is what occurs here in the Great Central Valley. When air rises, I'm going to give you a very simple, easy analogy, hopefully for you to visualize what this adiabatic lapse rate is. Imagine, if you will, that the air over your head, I don't know, some of you might be in Hanford or some of you might be in Visalia. It doesn't really matter, but the mass of air that is over your head, okay? Imagine it in your mind's eye as a big, tall drinking glass. The height of that glass represents that day's temperature. So today it's supposed to be about 100 degrees. So the glass would be 100 degrees tall. That's what I'm getting at. The weather guy is going to tell you that the humidity level is, say, 20%. So the glass is only about 1/4 to 1/5 full of water. In order to get that water out of that glass, you have to decrease the height of the glass. And that means you have to decrease the temperature. And there's only one way to decrease the temperature, and that's to make air rise. Remember, convection, frontal, now this is orographic. So you've got air that is going to rise. And as it moves up the side of the mountain, it will get cooler and cooler and cooler. And the height of that glass will continue to get shorter, 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 shorter. And eventually the height of the glass will be exactly equal to the height of the water that was in the glass. When that occurs, when the height of the glass and the water are equal, that is 100% humidity. That is when clouds form. The air is not capable of holding anything more than 100% humidity. There is no such thing as 110% humidity. That's physically impossible. The reason is, everybody, if you continue to decrease the height of the glass, do you see that the water in the glass will just continue to dribble out the side of the glass as you lower the height? Well, that's rain. So as air rises, everybody, there is no one, like, say, okay, when the air gets up to 2,000 meters, then it's going to automatically rain. That's not how this works. The adiabatic lapse rate works on the idea, everybody, that You have to consider what the humidity value of the air is. How wet is the air? What is the current temperature? Because the hotter it is, everybody, the more moisture that air is capable of holding. Cold air does not like to hang on to moisture. So as the air temperature decreases, because it's rising, eventually you will reach a point where it reaches 100% humidity. In the world of meteorology, everybody, and this will be a test question, by the way, anything less than 100% humidity is considered to be dry air. If the weather guy tells you it's 99% humidity on the 6 o'clock news, everybody, that sounds really wet, and it is. But from a meteorological point of view, from a science point of view, technically speaking, that's dry air. Clouds will only form when it reaches 100% humidity. Have you ever noticed that if on occasion, when you look up at the daytime blue sky, at sometimes you've seen clouds which you thought were, they were up there pretty high, but they're not real huge, not a big distance. Other days you'd look up and those clouds look like they were pretty darn far away from you, like they were way the heck up there. Well, you got to remember it starts with the air that's on the ground, just exactly how much moisture was in that air to begin with, and what was the temperature on the ground to begin with. And then as it rises, it's going to change in elevation depending on how much moisture was in there and what the starting temperature was. The rate at which you will eventually reach 100% humidity, it all changes. The height of it changes because of the characteristics of the air, okay? So this is why some clouds look to be much higher than others. Others look to be, lower, okay? If you see clouds that are like really low, this means that the air on the ground was really wet. And it did not take much of a temperature decrease to get all that moisture to form a cloud and then eventually rain on your head. So when you see really low clouds, you're in for a big storm. Okay. Now, adiabatic lapse rates on the diagram, I merely want to explain what you're looking at. I'm not going to make you solve any problems on the exam, okay? So what you're looking at there is 3 sets of numbers. One of them says temperature, one of them says elevation, and one of them says the letter T with a subscript D as in dog. What that means, everybody, is temperature dew point. And the diagram that I'm looking at is this one. There's 3 categories there. It says dry air. And remember, anything less than 100% is considered dry. So as you go up in elevation, the air temperature will decrease by 10 degrees Celsius every 1,000 meters. Once you reach 100% humidity, it's now wet air. Wet air likes to hang on to its moisture, so it will give it up a bit slower. So the air temperature is only going to decrease by 5 degrees Celsius every 1,000 meters. And the dew point will change by 2 degrees for every 1,000 meters that you go up the side of the mountain. Then I provided an example for you. Again, just an example. If you take a look at the bottom left-hand corner, it says starting conditions. This is a typical day in Visalia, 25 degrees Celsius, 9 degrees, the temperature dew point. So you got the height of your glass that is at 25 degrees. That's how tall the glass is. The dew point's at 9 degrees, which is less than half that glass. So the air temperature has to drop quite a bit in order to get that water out of the glass. So as you go up the side of the mountain, you do so in 1,000 meter increments. Because did you notice that on the top left-hand side, all three of those quick, easy formulas were in 1,000 meter increments? Okay. So you go up the side of the mountain in 1,000 meter increments. You start off with dry air. So you subtract 10 from the temperature and you subtract 2 from the dew point, and you come up with, what is it? 15 and 7. It's gotten a little bit cooler and it feels a little bit more wet to you. That's all. You go up another 1,000 meters and you subtract 10 from the temperature, that's 5, and you subtract 2 from the dew point, that's 5. Now you're at 100% humidity. Clouds will form at 2,100 meters in this example. Okay? At this particular point in time, I had to subtract 5 and 5 because as the height of the glass decreases, the water level has to go down along with the glass. So from 2,100 meters, you subtracted 5 and 5. Now your temperature and your dew point are 0 and 0. And what happens to water at 0 degrees Celsius? It freezes. So 3,100 meters is the snow level. And then you continue up to the mountain and you subtract 5 and 5, and the temperature and the dew point are both at -5 and -5 when you reach the top of the mountains. And in the metric system, everybody, the top of the mountains in your backyard is 4,100 meters. Visalia is located at 100 meters. Okay? When you now have cold air at the top of the mountain. Cold air is heavy air. So it's going to want to literally roll down the backside of the Sierra Nevadas. Once you got to the top of the mountain and you started working your way back down, the math changes a little bit if you hadn't noticed that. You're now adding 10 and 2. Because as the air moves downhill, it's going to get warmer and warmer. The pressure is going to build up. And so you're going to add 10 and 2 all the way till you get to the other side of the meadow over there. And if you'll notice, everybody, when you're at the other side, it's at 1,100 meters. And that's correct, everybody. The other side of the Sierras are actually up higher than you are here in the Central Valley. And so anyway, the temperature and the dew point, the temperature is the same as it is here in Visalia, but please notice the dew point. It's a heck of a lot drier on the other side of the Sierras. And that's the reason why. If you've ever driven a car up 180 or maybe 41 into Yosemite, what you should have noticed as you drove up the side of the foothills to get into the mountains, you saw fields, open fields of just ordinary prairie grass. But as you started to go up the foothills and gain elevation, you started noticing small shrubs. And then the small shrubs started getting physically bigger and more numerous. And then you started to see your first oak trees. And the oak trees were small to begin with, and they were spaced apart from each other. And as you kept going up the side of the mountain, those oak trees started to get bigger and bigger and more numerous and more numerous. And as you're driving up 41, everybody, those oak trees continue all the way up. They get bigger, bigger. And then all of a sudden, you're starting to see your first pine trees. There's just a few of them spaced far apart, but you keep going up and up and up. And then on 41, you come to a place called Oakhurst. That elevation, that's typically where the growth of oak trees stops. The oak trees can't tolerate being at the higher elevations, but the pines can. So once you get past Oakhurst, you see nothing but pines. And by the time you get to Fish Camp, you start seeing your first redwoods. And by the time you get to the gates of Yosemite, it's nothing but redwoods and pines all over the place. And there's just numerous. Well, as you go up the side of the mountain, it gets wetter and wetter. So it supports more and more vegetation. So this is why the foothill region is much, much greener than the valley floor. Okay, it rains on the side of the mountain. It doesn't rain over the Central Valley, not near as much. Okay. So on the exam, everybody, all you're really going to need to know about the adiabatic lapse rate is that you need to know that there's 3 mechanisms to raise air, because it will only rain on your head if air goes up. The first one was convectional lifting. The second one was frontal lifting. And now this third one that I explained to you with this little problem on the diagram was orographic lifting. And that's air that is pushed up the side of a mountain. Okay. Let's see here. Now, the only thing we have left on a study guide, it's when you look at the name, everybody, it's pronounced Keppen. Vladimir Keppen was Prussian by birth. That's basically East Germany today. And he is going to be one of the first ones in the science community to categorize all the various climate types that are found on the surface of Earth. He was also able to describe general characteristics of each of these climate types. So it's Mr. Vladimir Keppen that is going to identify 5 climate types. Now, they're all 5 of these are in the handout, and I've given you in the handout, everybody, all the characteristics that I want you to know right there in the handout. So you don't necessarily have to take notes from me right now at the moment because it's in the handout. So he's going to identify 5 climate types, and he starts out pretty simple, everybody. They're just categorized according to letters. There's a type A climate, a type B, a type C, D, and an E. If you should Google it, everybody, be aware of the fact that there is a type H climate. However, I am not bringing that up in lecture, and I'm not requiring you to know that for the exam. I'm just merely, some of you might possibly Google this subject and you're going to see, well, he said there was 5, but here the Google says there's like 6 or 7 of them. It has to do with the H type climates, and I'm not bringing that up in the exam. Okay. So the only characteristics I'll need you to know are A, B, C, D, and E, and F, or excuse me, A, B, C, D, and E, sorry. The A-type climates are, of all the 5 climate types, everybody, the A-types cover the greatest amount of surface area of the Earth. They make up 46% of the Earth's surface. That sounds kind of strange to you because that means almost half the Earth's surface is in the is tropical. Well, if you think about it, you live on a round object. Where is the greatest surface area on a round object? In the middle. So 46% of Earth's surface is classified in A-type. Now, before I begin even further, everybody, before I continue even further, this Keppen system that I'm about to describe to you is based on 2 things. It's based on average annual precipitation. And I use the word precipitation, everybody, because it includes rainfall, snowfall, sleet, anything that falls out of the sky. It's incorrect to say rainfall because you're just referring to rain. There's other things that can fall out of the sky. So you use the word precipitation, okay? So the average annual precipitation, the second thing it uses is average annual and average monthly temperatures. The reason it's based on precipitation and temperature, everybody, is because depending on what those 2 numbers are, that is going to dictate what grows naturally in your location. So naturally, the only thing that the Great Central Valley is capable of producing on its own without any intervention from man is tule grass, like prairie grass. And you've seen it all over the place because we don't get a whole lot of rain. And our average temperatures are a little bit on the warm side. And so we are a desert climate. So that is going to determine what grows naturally. Agriculture is not natural. Okay. So back to type A climates. It makes up the largest surface area of Earth. This is physically the largest vegetation on Earth. And by that, I mean it's the tallest and the leaves on the trees are the whitest. They are referred to as broadleaf trees. And the height of the forest canopy in the Brazilian rainforest is about 150 feet tall. That's tall. Some of you might have a pine or an oak tree on your property, and even the big ones are maybe just 50 feet. These things are 3 times that size. The general pattern of vegetation on Earth, everybody, is that the type A tropical climate supports the physically largest vegetation on Earth. They're the tallest, they're the widest, everything about them is physically bigger than anything else on Earth. So if you start from the equator and you move towards the polar region, the trees get continually shorter, 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 and the leaves get smaller, 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 smaller. Why? Because the angle of sunlight that you receive decreases and decreases and decreases as you move from the equator toward the polar region. So the leaves on the trees here in Visalia and the Central California are about the size of your hand. The leaves on the trees located in the Brazilian rainforest, everybody, are probably the size of your bed, if not bigger. So the vegetation is physically the largest. Another characteristic I want you to know is tropical soil is not good ag soil. And you might wonder, why is that when all that vegetation is there? You know, what are you saying? I mean, you got all this green located at the equator, so why is the soil so bad? It's precisely because of the high rainfall. That much rainfall rinses nutrients out of the soil, everybody. So the reason it's not good is because the soil is sterile. When soil is sterile, the technical or the scientific term for it is lateritic. It means that the soil is acidic. Okay. Now, plants have to eat just like you and I do. Now, we already know that part of their input, part of their food source is the sun itself. They photosynthesize, right? But they also require carbohydrates. So plants like to pull CO2 out of the atmosphere because it contains carbon. And when they process the solar energy with the CO2 that is located in the atmosphere, that's how they create carbohydrates and a waste product called oxygen. You are breathing plant poop. So anyway, the reason that these plants, where do they get their food source from? Well, you can well imagine that on the tropics, everybody, it's very hot and it's very humid. If anything dies in the rainforest, everybody, how soon do you suppose it would rot and decay under those conditions? It wouldn't take long. So even if one of these really big trees falls over in that rainforest, it is going to basically decay into the soil in a relatively short period of time. And this is going to feed the nutrients to some of these plants in the surrounding area. So in a way, the rainforest is almost like a cannibal. It has to eat just like everybody else does. So there has to be some form of nutrients in the soil. And with all that rainfall, vegetation in the equator, everybody, does not compete for rainfall. They got all the rain they can handle. What they're competing for, and this is why they're so big, is sunlight. These plants are growing taller and taller in order to maximize their exposure to the sun. So they produce these huge leaves to do just that. And so there's this competition amongst the vegetation to get taller and produce bigger, wider leaves. They're competing for sunlight. Okay. The second one are B-type climates. These are desert climates. A good portion of California is a B-type climate. The Central Valley is a B-type climate. In a lot of the characteristics that have to do with a B-type desert climate are very nearly the opposite of the characteristics of an A-type climate. The soil in the desert is actually some of the best ag soil on the planet. And the reason it's so good, everybody, is precisely because we don't get a whole lot of rainfall. So the nutrients that are in the soil are all still there. And they're relatively close to the surface. We don't get these huge rainfalls that either push the nutrients deeper into the soil or just flat out rinse them away down a river somewhere. We don't have that kind of rainfall here. So the nutrients are relatively close to the surface. And when I say nutrients, everybody, I'm talking about the sodiums, the potassiums, the calciums, nutrients, the vitamins that you take. Plants need this stuff as well. And when this stuff accumulates close to the surface, it gives the landscape a beige-ish tone and appearance to it. So if you hadn't already noticed, everybody, everything in the Great Central Valley is beige. So desert soil is actually good ag soil. The vegetation that grows in a desert is widely spaced apart from each other. And the reason is, if you remember, in the tropics, the vegetation is competing for sunlight. They got all the water they can handle. Well, it's the opposite in the desert. They've got all the sunlight they can handle. What they need is water. And so you don't see desert vegetation in big, huge forests because they're feeding off what little bit of water exists underground. So that will only support a few dozen plants. So in desert vegetation, they're actually very widely spaced apart from each other. And the Arab traders in the desert often called these places oases, because once they saw in the middle of the desert, if you see a palm tree growing, well, duh, there has to be water underneath there somewhere that the tree is feeding off of. The vegetation in the desert, everybody, in the tropics, I called it broadleaf. In the desert, they are needle leaf. They're trying to minimize their exposure to the sun. That's why they are needle leaf. These plants are also coated in a waxy substance. You guys know this. You've either grown succulents on your own property, or maybe you have a cactus plant in your house. They're coated in wax, and this is to preserve their water. Desert vegetation also produces a large taproot. So if you ever dig up a cactus or anything like that, they have a single root that goes straight down. And somewhere along that route, it's gorged itself with water. There's a big bulb. The root looks like a ball almost, and there's water in it. And that's what the plant is existing off of during a drought. So desert vegetation is actually good ag soil. It wants to minimize itself from the sun because they've got all the sun they can handle. Desert vegetation competes for water. The third type was Mediterranean, type C. Mediterranean climates are typically found on the west coast of large land masses. Parts of California are a Mediterranean climate. We are on the west side of a large landmass. And the kind of vegetation or agriculture that we practice here in the Great Central Valley, we specialize in vine crops and tree crops. That's what we grow. The country of Chile, the central country of Chile, is a Mediterranean climate. They specialize in vine crops and tree crops. They grow grapes, just like we do. And it's on the west side of a large landmass. Cape Town, South Africa, they specialize in tree crops and vine crops. They're on the west side of a large landmass. They grow grapes. France is on the west side of a large landmass. It's a Mediterranean type climate. What do they grow? Grapes, tree crops. Perth, Australia is on the west side of a large landmass. They grow grapes. For any of you in this class who are wine drinkers, this is typically where all the wines in the world come from. These various regions I just mentioned: Chile, South Africa, Australia, France, Italy, and California. We're all Mediterranean type climates. Most of humanity lives in a type C Mediterranean climate. Why? Of all the 5 climate types, everybody, a type C is the mildest. It's the only one that experiences 4 distinct seasons. The others don't. The 4th one is a type D. The outstanding characteristic of a type D, everybody, is that it's only located in the northern hemisphere. The 2 countries that are, for the most part, entirely type D climates would be Canada and Russia. That'll give you some idea of where a type D climate is located and why there is nothing in the south. Canada and Russia, everybody, are located at about 55, 60 degrees north latitude. If you look at 55 to 60 degrees south latitude, there's no land down there. So there's only type Ds in the north, okay? The Canadians refer to their climate type as the ecosystem that exists there. It's a boreal forest. It's basically a forest of spruce trees, Christmas trees. That's what they grow in Canada, Christmas trees, lots of them. Their economy is based heavily on wood-related products. Siberia is the same thing. It's a type D climate, and it's a big, huge forest. They don't refer to it as a boreal forest. The word in Russian is taiga, which is spelled Taiga, taiga. It's the same thing as the Canadian boreal. They just call it a different name, that's all. But it's only located in the north. The last one is a type E climate. Type B climate are polar climates, and type E climates are the driest of the 5 climate types. Type E climates are drier than deserts, okay? If you start from the equator and you move toward the polar region, the equator is very wet. It averages 80 inches of rain a year. That's an average. 80 inches of rain a year. When you move toward the polar region, the average annual precipitation value decreases and decreases and decreases and decreases. And by the time you get to the polar region, you're only averaging 3 inches of precipitation a year. Likewise, the average temperature at the equator is 80 degrees Fahrenheit. And as you move toward the polar region, the average temperature decreases until you get to the polar region. And the average temperature is 32 degrees, which is the freezing point of water. So even though it only actually snows in the polar region very little, what little bit does fall on the ground just never melts. So why is there so much snow and ice up there? Because you're looking at millions and millions of years of accumulation. Okay, do you remember me explaining, if you want to know what the atmosphere was like millions of years ago, you take a sample from the core of ice located at either polar region. Okay, so this particular climate type, polar climate, E-type climates, they only experience 2 seasons. It's either the light half of the year or it's the dark half of the year. The tropical A-types, by the way, only experience 2 seasons as well. It's either the wet half of the year or it's the dry half of the year. The C-types are the only ones that experience 4 distinct seasons. C-types are the mildest of the 5 climate types. And so again, this entire system, Köppen weather classification system, is based on average annual temperatures and average annual precipitation. Why? Because that dictates what grows naturally in your location. It's dependent on the average temperature and precipitation values. And so if you go to a place like Florida, it's warmer and wetter in Florida. Take a look at the ecosystem in Florida. It's a collection of Everglades. We are much, much drier. Okay. Does anybody have any questions so far? Here's what I plan to do tomorrow. Once again, as I said, exam 2, I'm going to I'm going to email out to you on Monday morning. Okay. So tomorrow I am going to go over the exam itself. So for those of you who are not here today, you might want to pay close attention to either me or the recording, whichever one, because I will go over the exam itself. Okay. And I will tell you exactly what it is you need to know and what, diagram, because there's going to be some diagrams on exam 2, and I will explain that tomorrow. Okay. So anyway, I will go over the exam tomorrow. All right. If anybody doesn't have any questions, I will see you tomorrow.
Thank you.
Bye.
Recording stopped.